Okay, thank you so much. Thank you for the invitation. It's a pleasure to participate in this workshop, albeit remotely. Indeed, I'll tell you today about geometric constructions for sparse signal recovery, specifically integer signal recovery. Okay, so let me start with some notation. So first I want to introduce the notion of a sensing matrix. So an n by d real matrix, where n is usually the smaller of the two dimensions, is said to be a sensing matrix for L sparse signals or L sparse vectors, where L is between 1 and n here. Sorry. If for every non-zero vector with no more than L non-zero coordinates, the image under A is not a zero vector. Okay. So this is actually equivalent to saying that my matrix A has the property that no L columns are linearly dependent. So such matrices are very useful in compressive sensing. So they're used specifically for robust signal recovery from few measurements. I'm specifically interested in a situation where the sensing matrices have integer coordinates. So the goal here is to have D, right, so the number of columns as large as possible as a function of n, while at the same time keeping the size of the coefficients of my matrix small. So now my matrix is an integer matrix. Okay, so why is this good? Well, so notice if I have if I have such a matrix, and say I have two vectors x and y with no more than L over 2 non-zero coordinates each, then if their images are equal, then the vectors must be equal, because you see, otherwise their difference would be in the kernel of A, but the kernel of A cannot contain any vectors with more than L non-zero coordinates. Okay. Great. So now the advantage of using integer matrices and integer signals is also that one can correct for an error. So because you see, not only you have this kind of restricted isometry property that AX equal to AY implies X equal to Y, but also the distance between any two images is relatively large, well, just because all of them have to be integers. So this allows for some error correction. So in other words, we have the following optimization problem. So we want to construct n by d integer sensing matrix for L sparse signals such that, first of all, the size of coefficients, so I call it the sup norm of my matrix A, is small. D, the number of columns, is large as compared to n, the number of rows, and the sparsity level, L, is as large as possible. Now, L naturally is always no bigger than n, but ideally I'd like to push it to be as close to n as possible. Okay, so that's the optimization problem. How can we construct such sensing matrices? All right. Well, so here's the first theorem in this direction that I'd like to show you. So this is joint work with Diana Needell and Lenny Sudakov back in 2017. So for all sufficiently large n, we can prove that there exist n by d integer sensing matrices for n sparse signals. So in this case, L, the sparsity level, is actually all the way up to n, with the following property. So the sup norm of A is equal to 1. So this means that A is actually a matrix with 0 plus minus 1 entries. And D is, well, about 1.3n. So more generally, if I take the sup norm of A to be K, then there exists such matrices with D being big omega of square root of K times n. Okay. So let me just quickly outline the proof of this theorem. So it's probabilistic in nature. So in particular, I have to say that an explicit construction of such matrices does not follow from our proof. Okay, but here's the argument. So first, we prove the existence of n by d 0 plus minus 1 matrices, with d being about 1.3n, so that every n by n submatrix is non-singular. This is our sparsity condition, in effect. Okay. So for this, we use a deep result of Bourgain, Wu, and Wood back from 2010, which says that if M sub n is an square n by n random matrix with entries 0 plus minus 1 chosen in the following way. So 0 is chosen with probability 1/2, and plus minus 1 with probability 1/4 each. So in this case, the probability that the resultant square matrix is singular is at most this. So 1/2 minus little o 1 to the power n. Now, I should say that since then, there was actually a stronger result in this direction. I believe Tikhomirov proved that the same is possible, picking 0 plus and minus 1, each with probability 1/3. But for our purposes, this is actually good enough. Okay, so, well, then we can form an n by d random matrix A, essentially taking 0 and plus and minus 1 according to this recipe. So 0 is probability 1/2, plus minus 1 was probability 1/4 each. So then, of course, I obtain a matrix with sup norm 1, and the columns distributed according to this M sub n law of Bourgain, Wu, and Wood. Well, then, what is the probability that that some submatrix is singular? Well, so for any n by n submatrix, the probability is about 1/2 to the n. Now, the total number of submatrices is d choose n, and so by union bound, the probability that there is at least one singular submatrix is at most d choose n times this 1/2 to the n. Well, so it's possible to bound the binomial coefficient, so using this binary entropy function, and then so using this bound, we can see that if we push d to be no bigger than about 1.3n, then then the probability that there is then this probability is actually less than 1. So this means that there must exist a non-singular matrix. So there. Okay, so that essentially proves the first part of our theorem. Now, for the second part, with arbitrary sup norm, we argue in a very similar way, actually. So now we assume that so the sup norm of A is K, and we want to prove that one can choose such an n by d integer matrix with sparsity level n, and D being big omega of square of k times n. So again, we use another result from the same paper of Bourgain, Wu, and Wood, which guarantees that that if now n sub n is an n by n random matrix whose entries chosen with equal probability out of the set from minus k to k, then the probability that the resultant square matrix is singular is at most this. Okay, so then again, we now build our rectangular matrix, choosing the entries according to now this capital N sub n law. So the probability that some resultant submatrix, that some n by n submatrix is singular is at most this, according to according to the Bourgain, Wu, and Wood theorem. Okay, so again, the total number of submatrices is D choose n, use union bound. So probability that there is at least one singular submatrix is at most this the binomial coefficient times this this probability. So again, using the same estimate and binomial coefficient, we can conclude that we can push D to be just a small multiple, sufficiently small multiple of square root of k times n, and then this probability stays less than 1, which means that we must have a that we cannot have a singular submatrix. Well, that there exists, I mean, a rectangular matrix with no singular submatrix. That's what I'm trying to say. Okay, great. So that's our first theorem. Now, one can ask, but how much bigger than n D can be? Well, so in this direction, we can prove that for any integer n greater or equal than 3 and k greater or equal than 1, there exists an n by d integer sensing matrix for n sparse signals. So the sparsity level is just the number of rows. So the maximal it can be with sup norm of A being k and D being at most this. So here you see the dependence on n has to be linear. So it cannot be bigger than linear. But here the dependence on k, the sup norm of A, is quadratic. Well, that that is not optimal. In fact, this result was quickly improved. This bound was improved by Kanyagin and Sudakov just shortly after. So they proved that for sufficiently large n, it's possible to take D to be big O of k times square root of log k times n. So you see it's so still linear in n, but an improvement in the sup norm of the matrix. Okay, so furthermore, they actually gave a deterministic construction of such matrices. So assuming that k to the power n over n minus 1 divided by 2 is bigger than n, then they showed that one can construct matrices with D being greater or equal than this bound. Okay, so great. Any questions so far? Okay.
I had a quick question. I was but maybe this is something for saving for the end, but I was curious. integer are these types of matrices that take just integer values, are they very common in signal processing, or?
Now, first of all, our framework is fairly new, so I don't know how many applications there are. Well, so in principle, compressive sensing definitely has applications for, medical imaging, for many things. So our thought process was that the integer matrices like this could be more useful for digital communications. So, for instance, for coding theory. But do I know specific applications? No, I don't. But I'm also not an applied guy.
Thank you.
Mm-hmm. Okay. So here's a question. So what is the optimal upper bound on D in terms of K and N? So in particular, is it true that one can, the D actually must be just a multiple of Kn? So in other words, in Kanyag and Sudakov's bound, the square root of log K can be stripped. So this we don't know. Now, just here's a simple low-dimensional example where, so here N is 3, D is 6, so K is 1, meaning that A is just a 0 plus minus 1 3x6 matrix. So this matrix has the property as we need it, meaning that no 3 columns are linearly dependent, and therefore it is an isometry on 3 sparse vectors. Okay. Right. So, but you see, the results that I showed you so far allowed the sparsity level L to be as high as N, the number of rows. But what if we allow the sparsity level to be smaller than N? So actually, in all the actual applications of compressive sensing, of which I know, the sparsity level is usually a lot smaller than N. So so can we do better? Meaning that can we make D bigger as a function of N if we allow L to be smaller? Okay, so here's my next theorem. So this is joint work with my recent student Alex Shu. So we're able to prove that for all sufficiently large N, there exist N by D integer sparse matrices for L sparse signals. Now, so in principle, our theorem allows L to be as big as N minus 1, so that now A has entries between minus 2 and 2. And now D is bigger, greater or equal than this bound. So this is the lower bound. Now, one implication here is that if I take L, so in principle, I'm allowed to take L as big as N minus 1. But if I take L to be small, so just little o of log N, then as N tends to infinity, D over N also tends to infinity. So this means that D is bigger than linear in N. So remember in all the previous results I showed you, D had to be just a constant multiple of N, whereas here it's bigger. Okay, so let me tell you a little bit about how to prove this theorem. But to do this, so to construct, and by the way, I should say that our construction, this construction is deterministic. So they're not just a probabilistic argument, but an actual deterministic construction, which is based on a certain geometric covariant problem, which I want to tell you about next. Okay, so here's a covariant problem. Suppose S is a set of k points in Rn. And say I want to cover it with parallel hyperplanes. How many hyperplanes do I need? Well, so it's actually easy to notice that the number of hyperplanes is no bigger than maximum of 1 and k minus n plus 1. So, well, now look, if k is less, well, if k is less than n plus 1, then I can cover the entire set by just one hyperplane passing through these points, even if they're in general position. Now imagine that k is bigger than n plus 1, then take n plus 1 points, pass one hyperplane through it, and then start sort of just translating this hyperplane parallel, so parallel translations until it hits the next point. Well, so maybe it hits just one point. So then you just keep moving it this way. So the maximum number of this kind of translations you still need is no more than this. Yeah. Okay. So well, so this number is sufficient, but is it necessary? So in other words, does there actually exist a set of k points that cannot be covered by fewer than k minus n plus 1 parallel hyperplanes? So we're specifically interested in this question on the integer lattice. So let me rephrase the question as follows. So suppose that t is an integer, so greater or equal than 1. And let me take this c sub n of t, let this be sort of an integer lattice cube with side length 2t, right? So the set of all integer points whose sup norm is no bigger than t. So now let S be some subset of this integer cube. Then one can ask, well, how many parallel hyperplanes does it take to cover such a set S? So now my set is on the integer grid. So first notice that so the 2t plus 1 parallel hyperplanes actually covers this entire cube. Yeah, because, well, just take a hyperplane passing through one of the faces and then just start moving it. So you will need 2t plus 1 parallel translations in total to cover the entire cube. So this means that every subset of this cube is covered. Okay, so here's also a lemma that is not difficult to prove. So suppose S is some subset of this integer cube of cardinality k. So first, if no fewer than k minus n plus 1 parallel hyperplanes can cover S, then k has to be no bigger than 2t plus n. And second, if 2t plus 1 parallel hyperplanes are actually required to cover S, then k has to be greater or equal than 2t plus n. So this means that sort of an extremal set, right, where this number of hyperplanes, 2t plus 1 hyperplanes, is necessary. So it seems like this set should have 2t plus n points. So this leads to the question, well, do such extremal sets actually exist? So does there exist a subset S of this integer cube of cardinality 2t plus n that cannot be covered by fewer than 2t plus 1 parallel hyperplanes? So, well, we can answer this question in the affirmative, at least in the case t equal to 1. So this means that, right, we have our integer cube consisting, right, of all integer points with coordinates 0, 1, minus 1. So we can prove that for each n greater or equal than 1, there exist these extremal sets, let's call them S sub n, of cardinality n plus 2, which cannot be covered by fewer than 3 hyperplanes. So notice, right, t is equal to 1, so this means that 2t plus 1, so the number of parallel hyperplanes I allow is 3, and the cardinality of my set 2t plus n is n plus 2 now. Okay, so one can prove that there exist such sets. So in fact, let me give you a couple examples. So here's one. So EIs are standard basis vectors. So take 0, all the standard basis vectors, and one more point, which is the vector minus 1, 1, 1, 1. This is a set of n plus 2 points, and it cannot be covered by fewer than 3 parallel hyperplanes. So here's another one. Take the vector 1, 1, 1, 1, and then in addition to it, just so all vectors like this. So this is for every I between 1 and n. So the sum of the standard basis vectors from n minus I plus 2 to n minus this. So again, just vectors with zeros, ones, minus ones, cooked up just right, so that they cannot be covered by fewer than 3 parallel hyperplanes. So both of these examples are actually special cases of a more general thing. So more general, I can take any vertices of any simplex containing the origin in its interior. So of course, in general, a simplex like this may not necessarily have its vertices on my integer cube, but any set of vertices of this simplex together with the origin will have this extremal property that I need. It will. I cannot cover it with fewer than what? What is my fewer than 3 parallel hyperplanes? Okay, great. So having such an extremal set, I can already from this cook up a very simple sensing matrix. So it's not great, it's not useful for any purpose, but at least it demonstrates a point. So suppose k is bigger than n, and suppose x1 through xk minus 1 are distinct non-zero vectors in Rn, and let S be this set. So now this is a set of k vectors because I'm also adding 0 to this set. So now let A be the n by k minus 1 matrix. So it consists just of the x vectors, not that I throw 0 out. But if S has this extremal property that it cannot be covered by fewer than k minus n plus 1 parallel hyperplanes, then A turns out to be a sensing matrix for n sparse signals. So meaning that no n column, no n by n submatrix of A is singular. Now, of course, so for in case of our sets, right? So here k is just n plus 1. So that's not very interesting because my dimension d turns out to be just 1 greater than my dimension n. So ideally, I want to do better than that. So this is just kind of a simple example, but with some more work, we can do better than this. Let's actually construct a different set starting from my set S. So suppose I take a set S of k points in Rn, and I partition it in two disjoint. So I partition in this, I partition in two disjoint subsets. So let's say I sub m, I sub m and j sub l. So m vectors in one partition, l in another, so that m plus l is k. So then let me build a different set. So xi minus xj, where xi's come from one partition, xj's from the other partition. So the total number of such difference vectors will be no bigger than m times l. Let me define, so suppose now I pick some subset of this total difference set. So the support of such a subset, what I mean by the support is just all the distinct vectors xi that appear in the differences. So for instance, suppose I take a difference set like this. So x1 minus x2, x3 minus x2, x1 minus x4, x3 minus x4. Here the support is just x1, x2, x3, x4. So I partitioned into, so on the one hand, I have x1, x3, on the other x2, x4, and I took the differences. Okay. All right, so one can actually build a bipartite graph from such a difference set. So let me call this graph gamma of D. So the vertices will correspond to the points in the support of my difference set D, and then two vertices xi and xj will be connected by an edge if the corresponding difference vector xi minus xj is in my set D. So in other words, D is the set of edges of my graph, gamma of D. So now let me write G of D for what is called the girth of the graph. So that's the length of a minimal cycle in the graph. So then let me write A of D for the matrix whose column vectors are elements of this set D. So then I have the following property. Suppose S, so the original set that I started partitioning to build my difference set, suppose S is a collection of k points. Now let me pick M and L to be integers, each greater or equal than 1, so that they add up to k, and I partition S into two disjoint sets, so M vectors and L vectors, and then let D be some subset of the set of all differences between I sub M and J sub L. Now let script L be, so script L will be my sparsity level. So let this be between 1 and n minus 1. So then the following two statements hold. So first, if S cannot be covered by fewer than k minus n plus 1 parallel hyperplanes, and for every subset of script L vectors from my difference set D, this girth, the girth of the corresponding bipartite graph is greater than L, then the matrix A sub D, right, whose columns are this difference vectors, is a Sensen matrix for L sparse vectors. So the second part is essentially the reverse direction. So if for every such partition, so ML partition, where M plus L equal to K, the resultant matrix from the full difference set is a Sensen matrix for n sparse vectors, then my set S cannot be covered by fewer than K minus n plus 1 parallel hyperplanes. So in other words, what we're trying to say in this theorem is that there is a certain bijective correspondence in some sense between Sensen matrices and sets that cannot be, so Sensen matrices which are built from this difference vectors and sets that cannot be covered by fewer than this than the sufficient number of parallel hyperplanes, K minus n plus 1. Okay, so this theorem is true for any set S of K points. Now, let's see. So let's see what this does for our specific sets, which were built on 0, 1, minus 1 grid. Okay, so so now essentially what I'm going to do is I will use this theorem to prove our original theorem. So let me remind you, the original theorem that I want to prove is, is this one. So it's the theorem that says that I can build sparse matrix, I can build Sensen matrices with sparsity level L and sup norm 2, where D is greater or equal than this lower bound in terms of N. Okay. So, and okay, so and I'm using this result. Okay, so there are some theorems by these three guys, Lebezhnyk, Ustimenko, and Walder, dating back to '95, about bipartite graphs, specifically about so this extremal bipartite graph with large girth. So meaning that remember, girth means the length of a minimal cycle. So they proved, in fact, they provided deterministic constructions of graphs of girth at least L plus 1 on K vertices so that the number of edges is greater or equal than this. Right? So essentially you take a bipartite graph on K vertices and you ask the question, well, how many edges can I throw in until I start getting relatively small cycles? So if I want to avoid cycles of length L or smaller, then I can still build a graph with so many edges. That's what they prove. So now let us take Sn to be so a set like those that I showed you in our example. So it's a set of n plus 2 vectors with 0 plus minus 1 coordinates that cannot be covered by 3 parallel hyperplanes. Now let gamma be, so I'm going to use this set Sn as my set of vertices. So now, using the Lebezhnyk, Ustimenko, and Walder construction, I can take a bipartite graph on this n plus 2 vertices, and so that the number of edges is greater or equal than this, so satisfies this this bound. So then I can take D to be the set of difference vectors which correspond to these edges of this bipartite graph. So this means that the girth of my graph is bigger than L. And so by our theorem, the matrix A of D, right, so this is the matrix whose columns are these difference vectors, is a Sensen matrix for L sparse vectors. And the sup norm of this matrix is 2. Furthermore, by the bound on the number of edges, D is greater or equal than this. And now, if I take L to be sufficiently small, so little o of log n, then D over n tends to infinity as n tends to infinity. So meaning that D is superlinear in n as I want it. Okay, so here's a simple example. So taking the set S3 in one of the two examples I showed you, I can partition the set into first 3 vectors and the remaining 2. So then compute the difference vectors and take the corresponding 3, 2 bipartite graph. So then here is a 3 by 6 Sensen matrix for 3 sparse vectors, since this graph does not have any 3 cycles. Okay, so that's all I wanted to tell you. So these are the references. The 2 papers we've written on this. Both of them are available on my webpage if you're interested. And thank you very much for your attention.